In this video, we're going to move on from our study of functions and formulas and graphs and get a little more sophisticated in terms of the tools we're going to use. We're going to start talking about words like continuity, limits, and derivatives, which are fundamental to the ideas in calculus. Starting with continuity, think about this statement for a moment. You were exactly at one point 1.00000000 meters tall. Think about that for a moment, and then take your best guess. I'm going to claim then the answer to this is that you were in fact at one point exactly 1.000 meters tall, and I don't need to know much about you to know that that's true. Let's see how we can provide some strong evidence for that. Imagine we have a graph that we can draw of our height over time. So time in years. And let's start down here at 0 meters tall or 0 meters long. And we'll put 2 meters up here. And if we put our birth height on there, which is I guess more of a length for a baby, but some height down here would be representative at 0 years. And if we put an age of, most of you are around 18, and you're probably somewhere around the 2 meter mark, a little bit above, a little bit below. In addition, we can add the line at y equals 1 meter. That would be here. And then we can ask the question, do we have to have been exactly 1.00 meters tall? Well, I think we do, because if we imagine starting at our birth height, we might have stayed that height for a while, then had an early growth spurt, and then maybe a little later on in life had another growth spurt. Notice we're crossed and had then a height of 1 meter at some point before we got to our current height. And it doesn't matter whether this was your height over time or whether you had a different profile. You will still have ended up crossing this 1 meter line. The only way to avoid that would be to have something much more surprising happen, such as starting at your birth height, growing for a while, and then suddenly overnight jumping from some height below 1 to some height above 1, and then going on from there. And so what we rely on to conclude that we must have been exactly 1 meter tall at some point is the continuity of our height over time. The fact that we wouldn't have a height that all of a sudden jumped and then the next second or the next instant we had a radically different height. We must have some continuous line describing our height over time, and if that's the case, we're going to cross the 1 meter line somewhere in our lifetime. Mathematicians formalize this into something called the intermediate value theorem, and it's essentially a paraphrase of what we just said in general terms. If we have a function that is continuous on an interval, let's draw this out. We have a starting point A and an ending point B. And we also have two function values. We have the function value at A to start with, and the function value B that we ended with. Then if we pick any number in between those two vertically, we'll stick with the same color scheme. Pick any height, and it doesn't have to be halfway in between. Let's, to make it more dramatic here, pick it as a value closer to the first red dot. Then there's at least one number C, and that's the value on the interval in X, where we cross the line. That's the translation here. Now again, we don't know, maybe the function goes like this and crosses almost immediately, and then goes up. That would be the point we called C. It may be that it happens multiple times. For instance, we might have a graph that does this. The theorem here simply guarantees that if we start on one side of this green line and end at the other, if the function is continuous, we will have to cross that green line, and we will be able to find a point where we cross that green line. Now this is interesting because we don't usually think about continuity when we draw graphs. We just draw the graphs. The fact that we can make these strong statements about existence is something that comes from some real deep understanding of what a continuous function is and what we can say about them. Going back to a bit more informal notation though, how can we characterize the graph of a continuous function? The most typical way people describe this is that it can be drawn in a single pen stroke. Or another way, a slight variation, is without lifting the pen. So both of these graphs here in red could be drawn without lifting the pen. Likewise for this black line graph, it could also be drawn without lifting the pen as well. It's also important to recognize that continuity is usually described over intervals. For example, if we say a function is continuous not just at a point, but continuous everywhere, an example of that would be, say, sine of x. Everywhere we draw the sine graph, it has the same shape over and over and over. One continuous pen stroke will draw that for us. Other examples would be polynomials. Any polynomial is a combination of integer powers of x. You can get quadratics and cubics. Those kinds of base functions are continuous everywhere. They can all be drawn as one continuous pen stroke. What else would we have? Exponential functions is another example. And even some other powers of x, like x to the 1/3, or the cube root of x, that would be a continuous function. As a quick sketch reminder, this is like the cube root function laid on its side, and it can certainly be drawn as one pen stroke. However, if we had x to the 1/2, or square root of x, that function would not be continuous everywhere because it's not defined everywhere. The square root function looks the same to the rough degree as the cube root function, but it's not defined over here. So we would say that function is not defined everywhere, and so it can't be continuous everywhere. If a function isn't continuous at a point or in a region, we would say it's discontinuous. And there's some fairly common examples for that. Tan of x is a big one related to the sine and cosine graphs. It has those vertical asymptotes every pi over 2, or starting at pi over 2 and then every pi after that. The graph continues like that. Another example of a graph that is discontinuous would be 1 over x. That graph has the asymptotes vertically at x equals 0, so it's not defined. We certainly can't draw it as a single pen stroke and cover those two branches at the same time. Here's a quick concept question. What about the function y equals the absolute value of x? Is it continuous at x equals 0? Take a moment to think about it, and then we'll dive in. Well, the best way to answer this is to sketch a graph. If we have x and y equals the absolute value of x, remember that when x is positive, the absolute value is the same thing back, so we actually get the graph of y equals x on this side. On the other side, if x was, for example, -1, we get a value of +1 back when we take the absolute value. That leads to a graph that looks like y equals -x on this side. And is it continuous? Absolutely. We can draw that as one continuous pen stroke. So we would say the absolute value function is continuous. Now there is something happening at x equals 0, but it's not a discontinuity. It's going to have something more to do with the derivatives and the ideas of slope at that point.